Good morning, ladies and gentlemen. Welcome to the sixth series of 2022 INA-IGS Geosynthetic webinar under the theme Designing with Geosynthetic for Environment of Roads. This event is brought to you by the Indonesian chapter of the International Geosynthetic Society, which is also known as INA-IGS. My name is Stephanie, and it's a pleasure to act as your master of ceremony of this event. Before we start, allow me to read the rundown of our event this morning. First, I will be reading the rules of the webinar. Second, there will be an opening remark by the representative of INA-IGS, Bapak Insinyur Doyolujeng Dwiarso MM. After that, the event will be guided by Bapak Michael Dobi as our moderator to start the presentation of our speaker, Professor Jehan. The event will then continue with a Q&A session. We would like to ask you to stay with us until the end of the event because we will be doing a quiz with a total of 2,500 rupiah for two winners. We will also give you access to the certificate at the end of this webinar. Ladies and gentlemen, for your own convenience, please put attention to the following rules. First, you can submit your question for the speaker to the Q&A feature located at the bottom of the screen. The question should be in English. Second, you can raise your question before, during, and after the presentation of the speaker. Third, we expect you to stay with us until the end of the event to get the information that you need regarding the e-certificate and also soft copy of the presentation from the speaker. Fourth, this event is also live streamed on INA-IGS YouTube channel, or you can directly go to the link bit.ly/live INA-IGS July 2022. Fifth, if you have any technical question, please contact Sandy at the number shown on your screen or on the chat box. Now, without any further ado, I would like to invite the representative of INA-IGS, Insinyur Doyolujeng Dwiarso MM, to give his opening remarks. Bapak Doyo, the time is yours.
Good morning for the participant from Indonesia, or good afternoon, or even good evening for the participant from other time regions. Distinguished participants, ladies and gentlemen, on behalf of the Indonesian chapter of the International Geosynthetic Society, INA-IGS, I'm pleased to welcome you to the 6th 2022 INA-IGS Geosynthetic webinar. This webinar is one of our series program organized by INA-IGS, the Indonesian chapter of the International Geosynthetic Society, in hope to distribute valuable knowledge in geosynthetics from respectable speakers to our members and, of course, to all of these webinar participants. I would like also to inform you that who missed of the series of these webinars, you can watch it on the YouTube channel by entering keyword INA-IGS webinar. For this morning webinar, I'm very delighted to have invited our insightful speaker who will talk about the topic designing with geosynthetics for improvement of roads. This respectable speaker is Professor Jehan, Ph.D. F.ASCE, who is Glenn L. Parker Professor of Geotechnical Engineering, the University of Kansas, USA. To Professor Jehan, Ph.D., on behalf of the Indonesian chapter of the International Geosynthetic Society, INA-IGS, I would like to welcome you to this webinar and also to express my gratitude for sharing your knowledge in geosynthetics and insight regarding today's topic with our participants today. And also, I would like to welcome you once again, all participants of this today webinar. Thank you for your participation, and I hope you can gain valuable knowledge from today's event. I also would like to thank you all committee of INA-IGS for your contribution in holding this webinar. Please enjoy the 6th 2022 INA-IGS Geosynthetic webinar. Thank you very much.
Thank you, Papadoyo, for your kind remarks. Ladies and gentlemen, now this webinar will be guided by our moderator, Bapa Michael Dobi. Before I give the floor to Bapa Michael Dobi, I would like to remind you that you can start submitting your question from now, during, and after the presentation by using the Q&A feature. We would also like to remind you to stay with us until the end of the event to get the information that you need regarding the e-certificate and also soft copy of the presentation from the speaker. Now, please welcome our moderator, Bapa Michael Dobi. To Bapa Michael Dobi, the time is yours.
Thank you very much, Stephanie. Now today I have the honor to introduce our speaker for the sixth webinar of this year, 2022. But before I do that and say a few words about our speaker, I would just like to thank, as usual, our organizers, as Pat Doyo did just now, who do a really wonderful job in arranging these webinars. And also, of course, to you, the attendees, the people who listen in, because we need your participation. We look forward to your questions at the end of the event. Okay, so our speaker today, Professor Ji Han. I'm sure that for many people, this name is well known, and I've been lucky to know Professor Ji Han for a little while now, and today his topic is going to be a road topic. As you are aware, the full title is Designing with Geosynthetics for Improvement of Roads. I think this is really important because in the previous 17 webinars we've arranged over the last 1.5 years, mostly it's been on structures and a few other similar topics, but we haven't had so many webinars about roads and road pavements and distress to roads, and this is what we're going to hear about today. Actually, our speaker could have spoken on many topics. His experience is very wide, and the material he has to present to us could probably fill a whole day of webinars. But anyhow, I asked him if he would speak about roads, and that's exactly what he's doing. As you've heard, and as you can read, Jihan is a professor at the University of Kansas in the US. In fact, he started his early life was in China, where he came from originally, in the area of Shanghai. He moved to the US to do his Ph.D, and he's remained there ever since. And I think during his career to date, he's made a really extensive contribution to both geotechnical engineering and to geosynthetics. So I have to say, perhaps for us people who work in academics of the quality of Jihan, who are doing this kind of work, because it helps support the ideas and technology that we develop in terms of geosynthetics, and we're definitely going to hear about that today. Also, as you can see, G has published many papers and delivered many important lectures in his career, which is an incredible contribution to these fields. G is a council member of IGS. And also he's involved in quite a few other engineering organizations, but from things a few years ago was to co-author a series of papers with J.P. Giroux on the topic of designing unpaved roads. And this is very nice because it now puts his name into the Giroux-Han design method, which is a very nice thing to do. And this is a design method by now. I was lucky enough to be invited to join a small team which was led by Jihan at the last international conference, and we conducted a workshop on road pavements. So the other people were Errol Tutumlua, who spoke a little while ago, and then the other one was JP Giroux. And this was really for me a fantastic experience, and G was our leader, which I'd like to thank him for again. He did a wonderful job doing that. And then the upshot from this was we wrote a paper which took a few years or so to complete, and we were guided by JP Giroux, which was another extraordinary experience, because anyhow the final paper is now you can get, if you're a member of the IGS, you can get to it through the IGS website. It's all there, plus all the accompanying information. Okay, so I've probably gone on for a little bit too long, but I'll just mention that this is G's first visit to Indonesia. He's coming to us in a virtual way, which is nice, but maybe slightly sad also. But I'm very much hoping that one day in the not too distant future, we might be able to welcome him to an IGS event or something similar here, and he actually comes to Indonesia. So that's about the last thing I'd like to say. I'd like to hand over to you now, G. I'm very much looking forward to your talk, and please, the floor is yours.
Okay, Mike, thank you very much for your kind introduction. And you mentioned about the paper we'll work together. I really enjoy work with you, and I also learned quite a lot from you. I would like to thank Indonesia chapter of IGS invite me to give this presentation. This is a truly honor for me, and I look forward to visit Indonesia in near future. Today, we'll talk about designing with geosynthetic for improvement of roads. In this presentation, I'll start with introduction, and then we'll talk about designing with geotextile for separation in roads. And then we'll talk about designing with geosynthetic for stabilization of unpaved roads. Then we'll talk about designing with geosynthetic for stabilization of paved roads. At the end, a few concluding remarks. But let me start with this true story. This is very interesting. And let's start with the words like walking and walking. And sometimes for me, it's difficult to distinguish the L and the R. But if you listen to my talk, if it does not make sense, L, maybe you should change to R. But for this case, actually, either way will be fine, walking or walking on the soft soil. So this is one of the projects I helped the local DOT here, the Kansas Department of Transportation, and we try to monitor the box culvert. This is a picture basically showing the inside the box culvert. And this was my student at that time to work for this project. But he went inside to the box culvert to install some strain gauge on top of the roof of the box culvert, and he stuck in the soil. But through the years, inside the box culvert, basically there's this very soft, sticky clay deposit on bottom of the box culvert. It's not very thick, it's about 30 centimeters. But he couldn't get out. But we handed the letter up, ask him to pull him out. Look, he said that like this kind of condition, I would not be able to work inside the box culvert. Then what we should do? And then he came up with some idea, say, hey, I know the beaver use tree branches to reinforce soil. Can we get some tree branches outside the box culvert, and we run out to collect some tree branches there, but not too many. If we put down there, of course, will not work. It's too few. And then he said, hey, we probably can buy some plywood. If this is plywood, we run to the plywood and then bought plywood, put them down. At the beginning, it was good, but this is too narrow and also getting dirty and it's very slippy. And that not work. And then he said, well, I learned some geosynthetic from you, right? Can we get some geotextile? Those are geotextile here. They put down the geotextile and he worked on it, it's still sinking into it. Okay, so you see the footprint here, it did not work. Then say, well, is there any other way? Okay, we got a Geogrid. But that's what he's standing on now on the geogrid. This is a stiff geogrid. Now, what's the difference between geotextile and geogrid? You know, geotextile is very flexible. The stiff geogrid has a little bit bending stiffness, but just because of that bending stiffness is enough to support him, the weight of the one person, and then he finished that job, okay? But this is kind of trying the error with basic knowledge of improvement, right? He knew the soil is too soft. He couldn't walking on this soft soil, but needed some reinforcement or improvement. And then find different way. Eventually, we find a solution. But is this a state of practice? Of course not. But let's take a look at what the state of practice for pavement design. This is kind of transition. We start with some kind of empirical design method. We'll talk about that a little bit later on. Basically, based on the statistical analysis method, back 1950 in Illinois, in US, they tried a lot of truck testing, and they developed design method for that. Okay, now kind of we are moving towards this is a mechanistic. Mechanistic basically is a theoretical, okay, based on the mechanics, and then this is called mechanistic empirical. There's some portion mechanistic, some portion is empirical. So this is kind of like state of the art. So what is state of practice? We are in the transition from empirical design method to mechanistic empirical design method. So I will get into that in the lecture. But this is the method called 1993 AASHTO Design Guide, the statistical-based method. But this is the AASHTO Mechanistic Empirical Pavement Design Guide called MEPDG. Was developed, about 20 years ago. So here, basically, state of practice. Okay, let's take a look at common distress of roads. So let's start with unpaved roads. Unpaved road means there's no pavement surface like asphalt or concrete. But there are two different situations. One, on the construction side, you may have a heavy vehicle and go on the road to carry, aggregate, carry other material, generate pretty large rutting. But this is like a local road, also called gravel road. And also, after use while you may get some rutting like this. But rutting is the major problem for unpaved road. Now, how about asphalt pavement? There are two common problems. This is one, basically also rutting, even though pavement is stronger than the gravel, but with larger number of traffic, you still can get the rutting like this, okay? Or you can get the cracking like this. This is mostly like a fatigue cracking, okay? The rutting, fatigue cracking, those are the two common distress for asphalt pavement. How about concrete pavement? The concrete pavement mostly failure happen close to joints. But this is basically transversal joint due to less support at the joint. If you have the tire sitting on this location, and you will create some kind of joint crack like this. Another problem with the durability. Basically, this is a cold region. Water can get into the joint and then get saturated. The concrete get frozen and then expansion and then salt and create some kind of durability problem with that. But joint cracking and durability cracking are two common problems with concrete pavements. Now, so far, geosynthetics mostly used to improve the unpaved road, improve asphalt roads. There are few applications use geosynthetics to dealing with concrete pavements. But in my presentation today, I will focus on the unpaved road application, asphalt road application, but we're not talking about concrete pavement application, even though I've been doing some research on this area. Okay, let's start with the basic parameter called California bearing ratio, called CBR. But this is a common parameter used for pavement design. But let me explain a little bit about this parameter. But you probably familiar with the compaction mode. That you put the soil there, you compact into layers, and on the top you put the weight there, and then there's opening, there's pistols to push the piston down into soil. Then you will measure how much load required to push like a 0.1 inch or 0.2 inch. That's equivalent to like 2.5 millimeter or 5 millimeter displacement. But that force will be used to divide by the force required to push pressure stone. the crushed stone is considered as a standard material. But if the ratio basically is defined as the California bearing ratio. So let's say if you have CBR equal to 1 or 1%, that means the stiffness of this soil is about like 1% of the crushed stone stiffness. Okay. If you understand that, but this is the Illinois DOT has some design guideline, say, under what kind of subgrade condition you need to take some remedial procedure. Okay, so take a look here. If CBR less than 6, basically this is 6% of the stiffness of crushed stone, you definitely need to take some action to improve the soil. Okay, now if greater than 8, you don't need anymore because the subgrade is strong enough, and you don't need to make an improvement. But between 6 to 8, you depend on the situation. Sometimes you need, sometimes you may not. But that is one number. CBR if less than 6, you need to improve the subgrade. Okay, but there's one guideline developed by Geosynthetic Manufacturing Association US called GMA, and provides some similar guideline, but they have 2 different situations: CBR's unsoaked, CBR soaked. But for situation, if your road was subject to rainfall, probably uses soaked CBR. That is the one typically we use for design. But in other words, if you have a CBR greater than 3, the subgrade is reasonably strong, and you only need to use non-woven geotextile as a separator or separation. Okay, but if the 1, 2, 3 they get weaker, then you need the reinforcement. Then you need to use Geogrid or woven geotextile. Now, if this subgrade even less than 1, that is very, very soft. For that case, you not only need the reinforcement, but also need the separation. Okay, but for Geogrid, you also need to use non-woven geotextile underneath the Geogrid. Otherwise, the soft soil was squeezing through the aperture. Or you can use the woven geotextile. But here, basically, the materials, and probably you're all familiar with most of the material on this slide, this non-woven geotextile, this woven geotextile. Now, this is a special geotextile called Wicking Geotextile. Those white fiber, they can create the suction, and it can suck the water into fiber and take it out, evaporate. But we have been working on this product for, I don't know, 5, 6 years, maybe more. And I will not talk about this in this presentation. And if you're interested, maybe I can give you another talk specifically about Wicking Geotextile. But this is a GeoNet, mostly for drainage purpose. And as you know here, the 3 different kind of geogrid: the biaxial geogrid, triaxial geogrid. This is a multi-axial geogrid. This is a brand new product. And basically, unique about this product, I don't know you know this or you realize this, basically they have 3 different actual shape and size. See here, this is triangular, this is this one, trapezoidal, and this is this shape. Okay, the reason create those different size, different shape, basically improve the interlocking between the aperture and the aggregate. Okay, all those products basically is called planarly reinforcement or geosynthetic. So the last one, basically, geocell is a 3-dimensional reinforcement, basically with height. The soil inside the pocket will be confined, and that is the geocell products. In terms of application, as I mentioned early on, we will use for unpaved road, the paved road, mostly dealing with asphalt, but you also maybe use for concrete as well. And typically, we place the geosynthetic at the interface between subgrade and the base course. As you can see here, this is the geotextile, and this is the base course, and there's a geocomposite below, and the base course, and then this is shows the geocell. Okay, but this is for construction platform situation, and this is a similar. But if the base course get very thick, sometimes you will put another layer there, okay, to stabilize the base course. Okay. In terms of function of geosynthetic in road, and geosynthetic can be used for separation and mechanical stabilization, lateral restraint as confinement. I will spend a little bit of time talk about this, and this is a little bit different from the reinforcement as I mentioned earlier on. And that reinforcement used for slope stability, for retaining wall, and for embankment applications. But for roadway applications, it's a little bit different. But we came out with the different terminology or different function called mechanic stabilization, and the filtration, drainage, and the barrier. Okay? So let's take a look at the mechanisms and the benefits. Let's start with this one. The first one was separation, basically separate the subgrade material and the base course material, basically to prevent the intermixing of those materials, right? That you can keep the base course clean, keep the base course, just like before. There's no containment from the fine material from bottom. But there's another situation, and we can use some kind of geosynthetic. For this case, is like a wicking geotextile to prevent the cable rising into the base course. But especially if you have a base course with fines, and they will attract the water from subgrade. If you place the geosynthetic, the wicking geotextile here, will stop the rising. The reason wicking geotextile will suck the water downwards and take out the evaporate. Okay. But for those two mechanisms, basically maintain the strength and modulus of the base course, because you try not change the moisture content here, you try to not change the fine contents here. Now, this is the typical application, basically tension membrane, that when we have the tire sitting on the road, we develop some kind of differential sediment, and then geosynthetic will develop tension. Okay? The vertical component of the geosynthetic basically will carry the load. But that mechanism basically we call tension membrane. This also refers to the reinforcement function. But if we have a soft subgrade, so we talked about earlier on, the subgrade will start to heave up under the loading. If you have a geosynthetic here, we provide called vertical restraint, basically not allow the soft soil to heave up. That will increase the bearing capacity of subgrade. Another thing is here, when you place a geosynthetic here, suppose this slip surface maybe can go deeper, okay? Because of the geosynthetic, they limit the slip surface go deeper, they will increase the bearing capacity of base course. Now for this mechanisms, basically increase strength of the subgrade and the base modulus. There are two more things. One is the lateral strength. What is the lateral strength? Because under wear loading, we're dealing with aggregate base. Aggregate base will start to lateral spreading. If you have the friction from geosynthetic, and then can minimize lateral spreading, and also can reduce the deformation from the wear loading. Okay. The last one basically is kind of drainage. That you can place a drainage layer, the water can drain out, that will reduce moisture content here. So for those two mechanisms, basically you increase the strength and also modulus of the base course. Okay. Now, the two things, tension membrane and the lateral strength has been subject to debate about what's the difference between those two. And we came out with the idea, tried to separate those two mechanisms through this equipment. But this is the test setup called trapdoor test. But you see there's a door underneath here, there's the plate. That we can load the plate and just to see what kind of deformation above this. And also we can place a geosynthetic there, we put the strain gauge there to measure what kind of tension develop on the geosynthetics. But this is the illustration. But this is the trapdoor. But during this test, we load the trapdoor first. Okay. And then we measure the strength distribution just like this. Okay. There's a strength distribution. But this is at the edge of trapdoor, and you see very large tension develop at the dislocation because there's a tension membrane effect develop. Okay. Now after we load down the trapdoor, then we stop and then we fix it. Then we apply the load from top, then generate lateral spreading. Then see what kind of tension will generate in the geosynthetics. Okay. But that's what we see for the first one. In order to mobilize the tension membrane, you have to have an anchorage. If you don't have an anchorage, you will not have a tension membrane. Then after we apply the load, you see that the change of the stress in the middle. Okay, you will not change the tension here, only in the middle. That because of the lateral restraint. Okay, the tension membrane requires large diffraction, larger tension, and anchorage. Okay, those are the three things for tension membrane. Now let's talk a little bit more about lateral strength. The actual lateral strength mechanism was observed or was proposed by Hilberton back in 1981. When he described the wear loading and generally lateral spreading, eventually generally the shear stress on the geosynthetic, but also generally the tension in the geosynthetics. Okay, but if you read carefully about this drawing and you see there is another direction, and outside this direction, actually they generate the compression. Okay, so you have a zone of tension, and then outside there will be some kind of compression. Okay, the numerical analysis actually observed that behavior. This is numerical analysis was done by F.ASCE, and compared to different kind of Geogrid apertures. This is a biaxial, this is triaxial, and the wear load. As you can see, the red in the middle, red is tension, blue is a compression outside. As you can see, for this lateral strength, you don't need the anchorage. As you know, geosynthetic typically cannot carry high compression. But even you cut the geosynthetic at this portion here, will not affect the geosynthetic to resist the lateral spreading, because the compression strength will not add much resistance to the load. Okay. Another thing I want to point out here, but this is how much tension basically calculate in the geosynthetics. For this product, if you recognize this product, this is a 20 kilonewton per meter product, but you only mobilize 2.5% strength for this case. Okay, how about this one? Okay, this one, the stress is even lower, and the only 1.4% strength mobilized. Okay, but for this case, as you can see, because the triaxial geogrid, they have a better shape to distribute the load in the ribs. But you only get almost half of this tension under the wheel. But another point I want to make, basically, you don't need much strength to resist this load through the lateral strength. But the stronger product is not necessarily better. Okay, but to be effective in lateral strength, a geosynthetic must interact well with soil. Okay, be strong enough not to break. Okay, and also durable enough to maintain its shape and function. But the strength of the geosynthetic only need to maintain the shape of the geogrid. There's no need of very high strength. Okay, let's take a look at this case. The Professor Brown in UK, he did the study. It's a very interesting study. He dealing with a railway application. But you have the loading plate, the cycle loading. You have a geogrid here. He only dealing with the biaxial geogrid and with ballast. And then he measured the sediment after 30,000 load cycles. And those number here, okay, those number. What are those number? This is the 40 kilonewton per meter tensile stress of the geogrid, okay? And that one deformed the most. And then this one is 20 kilonewton per meter geogrid, and it deformed the least, okay? The stronger product does not necessarily mean better, okay? The better is basically he found out the aperture size. The aperture size somewhere here interlock better with aggregate the size, the maximum size is 50 millimeter, mean size is 38 millimeter. But he found basically this optimal aperture size as compared with aggregate size. But he came out with some number saying the aperture size, if it's 1.5 times the maximum particle size, or aperture size 2 times the mean particle size, that reached the optimal situation, basically interlock the geogrid with aggregate. Okay? But unfortunately, high strength, high resistance does not result better performance. The performance depends on geogrid aggregate geometry compatibility, basically aperture size divided by the particle size. Okay, now let's take a look at the comparison between lateral strength and the tension membrane. Then we talk about lateral strength early on, basically under the load, the particles have a lateral spreading, generally the shear stress, over the shear stress, the tension in the middle, and outside compression, okay? But that basically mechanism typically refer to mechanical stabilization. Now, typically happen at the small deformation, okay? You do not need a large deformation. Now, different from that, as I showed earlier on, with tension membrane, you have a very large tension, you need a large deflection, and then also you need the anchorage. Without anchorage, you will not have any tension developed in the tension membrane. But this is basically for reinforcement effect, okay? But this requires a large deformation. Now, the tension for the tension membrane is much higher than the tension required for lateral strength. But they can transit from one situation to another situation if the deformation getting larger. Basically, when the deformation gets larger, the lateral strand may become the tension membrane at the end. Okay. Now, lateral strand is more effective than the tension membrane because the geosynthetic is the same direction as the load. As you can see here, this load generated shear stress is in the same direction of geosynthetics. But if you look at the tension membrane, the load is 90 degrees to the orientation of geosynthetic. This is why tension membrane is not that effective as compared with lateral strand. Okay. But for most applications in the roadway, actually, you may have a different kind of mechanism. You may have a separation, you may have a filtration, you may have a reinforcement, you may have the mechanical stabilization all together. This is why geosynthetic may serve different functions in the roadway application. Therefore, a generic term improvement may be used for combined functions. Now, in order for geosynthetic really work, first, you need to make sure the geosynthetic can survive the construction. Now, for this case, you see they use a very large stone and dump on the geotextile. I'm not sure whether geotextile will survive. But this is one thing we also need to consider when you choose the geosynthetics. The resistance to site-specific destructive force applied to the project construction and the surface operation should be considered. But that relates to the condition of what kind of subgrade you may have, what type of a cover aggregate you have, or the thickness, and the ground pressure of the construction equipment. Okay, but geosynthetic can function and provide benefits only if it survives. Okay, the Federal Highway provides some guideline for you to consider what cover thickness you may use and what geosynthetic product you may use. Number one means this is a stronger product. Two means this is a weak product, basically the class 1, class 2. But here basically show you the subgrade. As you see, if you have a little bit stronger subgrade, then you can use a lighter or weak geotextile. Now, for some situation, if the subgrade is very soft, the CBR less than 1, then you may not be able to construct with geotextile if the thickness is too small. Now, for this case, they suggest you need at least 450 millimeter, and in order to carry the tie pressure greater than 350. Okay, but you also need to use a strong geotextile. But that actually provides pretty good guideline. As I mentioned, geosynthetic class 1 is stronger than class 2. Now, what kind of requirement for Geogrid? But this is basically dealing with Geogrid, and as you can see, and for Geogrid, not only you have a class 1, 2, 3 with a different strength, but they also need to make sure the aperture size. Okay, but you see here the aperture size basically need to be between this size range. Also need a greater than mean size, should be 2 times less the D85. But this is similar to the results the Professor Brown got for his study. Another thing, this is basically to make sure that you have a better interlock. But another thing we need to consider regarding the separation, because the Geogrid has openings, that we need to rely on aggregate to provide the separation function or filtration function with that. Okay, but if you don't have that aggregate, then probably you need to use a geotextile to serve as a separator. Now let's move on, talk about the design for the 2 different applications, one dealing with unpaved roads, one dealing with paved roads. But here basically show you, as we know from the Mechanistic solution, if you apply stress on the top, the stress will decrease with that, right? But the decrease of the stress for unpaved roads is different from paved roads. The reason, because paved roads, you have a stiff layer on the top like asphalt, right? And then you have base course, you have subgrade base. But for unpaved road, you only have an aggregate. But for that case, if you apply like 600 kilopascal, then at the bottom of the subgrade, you may still have 100 to 200 kilopascal pressure. Then for that high pressure, the subgrade may fail if it's not strong enough. So what is the important parameters? Andreas shear strength for that case. The major failure, the distress is rutting, as I mentioned earlier on. Basically, it's a bearing failure. So for this case, basically, it's a strength-based design. For paved road, because you have the stiff layer asphalt, you have base course, you have subbase, eventually get to the subgrade, the pressure will be 10 to 20 kilopascal. So for most cases, you don't have a bearing capacity problem. However, you may have a compression problem, okay? The compression is related to the parameter called resilient modulus. We'll talk about a little bit later. For asphalt, also attract the tensile stress at the bottom of the asphalt, okay? So the failure modes, as we talked about earlier on, the rutting and the fatigue stress. So how do we determine the resilient modulus? Basically, you need to use a called dynamic triaxial test. You have a confining stress, and you can generate the cyclic divital stress. So from that, you can calculate the resilient modulus. The paved road design is typically a deformation-based design, but it's different from unpaved road. Okay, but here basically show you typical performance with rutting, with number of passes. For unpaved road, you will have some kind of bearing failure at the end, may fail because of base or may fail because of subgrade. Now, for paved road, basically this is called resilient behavior. They will have a cyclic behavior, but you will have a stable base of subgrade. Okay, but this is strength-based design. This is deformation-based design. The unpaved road allow large rutting are designed based on strength, while paved road allows small rutting and are designed based on deformation. So let's talk about the concept about the elastic deformation, permanent deformation, and the resilient deformation. Okay, so this is a triaxial test, and this is basically divital stress, axial stress. If we have the first cycle, the load this control without geosynthetics, and then you would measure called elastic modulus, right? This is elastic deformation. Then if I remove the divital stress, you will unload it, and then you can measure another modulus. This is called resilient modulus or rebound, okay? Basically, this is resilient deformation. Now, you can see now the slope is not same, okay? Typical resilient modulus is greater than the elastic modulus, okay? The resilient modulus is defined by the divital stress divided by strength. And then if we have geosynthetics, because when you push, you have the geosynthetic lateral restraint, you provide additional confinement stress, you will get this curve basically with a smaller deformation and a little bit larger elastic modulus. Okay, then you unload again, you get the resilient modulus. Now, what happened here for the first cycle, you will find out that the elastic modulus for the improved case will be greater than the control case. However, will be less than the resilient modulus. Now, if you compare those two resilient modulus for the control section and the improved section, actually their resilient modulus is almost the same. Okay. Now, this may surprise to some people, and I'll explain to you why. Okay, let's keep going, and with number cycles, and you now get the loop getting smaller. Okay, this is basic control, and this is the improvement. And for that case, elastic modulus is close to the resilient modulus. But still, for the control case, the resilient modulus is almost the same as the improved resilient modulus. The reason, because resilient modulus is defined as divital stress divided by the resilient deformation of rebound. As you know, when you release a load, when the specimen starts to rebound, the horizontal geosynthetic cannot restrain the vertical movement. But this is the reason. The reason geosynthetic cannot increase measured resilient modulus is that resilient strength is perpendicular to the geosynthetic orientation, so that the geosynthetic cannot provide any vertical strength during the rebound. Okay. So what do you end with? This is a control like a total deformation. and then you have a permanent deformation. Okay, but that difference basically is the linear deformation. That if you improve one, basically you have total deformation here and the permanent deformation here. Then eventually you get the larger reduction of permanent deformation. Okay, but this is an important point here. Geosynthetic is more effective to reduce accumulated permanent deformation than elastic and the zero deformation, because elastic and zero deformation only happen for individual cycles, but permanent deformation accumulate, and also because of the accumulated lateral strength minimize more permanent deformation. Okay, but let me show you the results. If you don't believe the geosynthetic will not change the zero models, this is what we have. But we did study with experimental study, with analytic study, both show basically the geosynthetic will not change the zero modules of the specimen. However, they will reduce the permanent deformation, as you can see here. This is a non-stabilized samples. Those are stable samples. Okay. Okay, now let's move on to talk about the design method, the mechanistic empirical design method, as I mentioned earlier on. And this basically is the new design method. This is a very comprehensive design method, can consider climate, can consider material like a pavement surface, base course, can consider traffic loadings, and from traffic loading can calculate the stress strain respond, and then use this accumulated damage, okay? And then from the accumulated damage, basically like a plus strain, and go to the distress. But this is empirical. As you can see here, from this portion, this is mechanistic. From this portion, this is empirical, okay? And included the accumulation is empirical. But this is what I call mechanistic empirical design method. Okay, mechanistic, empirical. Okay, so let's talk about the layer elastic theory. The famous solution was developed by Burmans back in 1945. But let's start with the stress on top of surface, and then you calculate the stress at the depths, okay? And if this is a uniform material, you can use the Boussinesq solution as you learned from soil mechanics. The shape look like this at the center with the largest stress, and go to distance, we get the small stress. Now, what happened, typically we use called stress distribution method to simplify the calculation, right? And that's stress distribution. Now, if we have a pavement, what happens is E1, basically the pavement modulus is greater than subgrade modulus. Then you create a situation, basically Burmans solution, layer elastic theory, and he calculates the stress get reduced because of the stiff layer. But now it's a stress like this. But if you still use the stress distribution method, then your distribution angle getting larger. Okay, but that's the stress reduction, and also increase the distribution angle. So we did some study to measure the vertical stress for one case with the asphalt pavement, base course, and without the geosynthetic, with geosynthetic, how the vertical stress change. This is the also Burmans solution, as you can see. Basically say if we have the depth here, the Burmans solution, the stress at this location, if we increase the modulus to 5, basically you reduce the stress to this location, okay? But that is a benefit by using stiff layer on the pavement. But our results basically show this is the control section measure high stress, but if we use a geocell with same thickness, you get a reduced stress by almost half or more, okay? But indeed, the geosynthetic helped reduce interface vertical stress, okay? Now let's talk about design with geotextile for separation in roads. And as we know, for this case, there's no separation, but the basic subgrade and the base course, they intermix, but you generate very large rutting, okay? Now, if we place the geotextile there, but this is a very nice test. Basically, this section here with geotextile, this section here without geotextile, as you can see, for this light color section with geotextile actually indicate very good separation. The rutting depth is very small. But if you come to this side actually you generate very large rutting. Okay, the geotextile does separate between the base course and subgrade. Okay, so how do we design for this? And Federal Highway has some kind of design guideline. This is based on experience data. Basically said, this design chart can help you to estimate percent of aggregate loss in the foreign empirical graph was developed based on the observation of the unpaved road without the geosynthetics. Okay, but let's say if I have a subgrade CBI equal to 2, if you go there, basically you will have a 30% aggregate base will be lost. So if I use some number here, if the base course is 30 millimeter, 2%, 30% loss, your remaining base thickness will be 210 millimeter. Of course, it will not perform as what you designed because you lost the aggregate into the subgrade. Okay, the use of subgrade geotextile separator prevent this aggregate thickness loss. Okay, now if you want to design the geotextile for long-term performance, the filtration criteria should be met. Okay, so here basically show you some picture with the asphalt pavement. As you can see, if there's a crack, the fine migration will come up. How to fix this problem? Place the non-woven geotextile before you place the aggregate base, before you place the asphalt. Okay, the use of geotextile separator prevents the loss of fine from subgrade. Now here is the real study in Oklahoma DOT, not too far from Kansas. The original design, this is traditional design, they use a 60 centimeter line treated subgrade before they place aggregate base, and then you have chip seal layer on the top. Now they changed this, say I will not treat the subgrade. Instead, we place non-woven geotextile before you place aggregate. So basically, you use non-woven geotextile to replace 60 centimeter the line treated subgrade. Okay. Now they excavate after 5 years and the 15 years. That's what you see the excavation, and this what you see after 15 years. This geotextile still perform very well, and also you can see those weaklings stuff there. But that also proved there was no tension membrane happen on the pavement. As you see, if you use tension membrane, this will stretch out, right? But the fold is still there. And another thing they found out, the particle basically can't stone the impression on the geotextile and basically interlock with geotextile, basically provide the lateral restraint. Okay, but this project actually, the geotextile option only costs like 1/3 of the cost of a lime stabilized section. That saves a lot of money for that project. Okay. Okay, now let's move on to talk about design with geosynthetic for stabilized of unpaved road. But there are many different design methods available, and mostly based on the strength method. But in this presentation, I'll focus on the 2 methods because of the time limit. But those are strength-based method, and then we developed some deformation-based method as well. Those are my former PhD students, and we will not have time to talk about those, but we will talk about those 2 design methods. Okay, but start with the Stoke method. But this method is very simple. But they assume this is uniform layers. But does not distinguish between base course and subgrade. But use the Mechanistic solution to calculate vertical stress here. But make sure the vertical stress is less than the bearing capacity, NC times Andre shear stress. Okay, but this is strength design. The NC is the bearing capacity factor, depending on whether you use a geosynthetic or not. For that case, geotextile, then you will lower bearing capacity factor. With geotextile, you will have a high bearing capacity factor. Another thing they found out, if you have a larger deformation, you will mobilize higher bearing capacity factors. Okay, so if we take an average for that, typically we design for 75 millimeter rod depths, and let's say bearing capacity for without geotextile is 3, with geotextile 5.5. But they developed a design chart to help engineer to design, to select the thickness of base course. Okay, but here's the example. This based on the single wheel load, 45 kilonewton. If like 2,000 passes, if subgrade is 1% CBR, we can estimate the under shear strength is 30 kilopascal. And if you use without geotextile, use the bearing capacity equal to 3, the C times NC equal to 90. But you can come to here, if you use geotextile, use 5.5, but that C times NC is 165. But if you come to this figure, it's dealing with a single wheel load, if 90 come down to the curve with a 45 kilonewton wheel load, you determine what is the thickness base course you need for without geotextile, 475. Now, if you use the 165 with geotextile, come to here with the same wheel load, you come out the thickness now is equal to 325. But you get the 32% base course thickness reduction. But it's a very simple design procedure. You can do that. Okay. So as Michael mentioned about Dr. Giroux and I worked together, published 2 papers in 2004, basically developed a design method for geogrid reinforced unpaved road. And this method has been included in the Federal Highway Design Manual. So I would like to spend a little bit of time to talk about this method. The first in this method, we'll need to check whether the base is strong enough to carry the load. And this is a design chart that you may use to estimate whether is base strong enough. But let's say this, I apologize, this is the English unit we use here, but 100 PSI, high pressure, and with single wheel load, the 10 kips. If you go this, if you find out what the base CBR, then you can know what the number of passes can carry. For this case, 10,000 passes. The base should be strong enough to support the traffic. All designers assume base is strong enough. Okay. But now, also we use the stress distribution method to calculate the stress at the interface between the subgrade and the base course. The difference from the previous method, now we consider the distribution angle depend on the modulus ratio. The base modulus divided by the subgrade modulus, and you can calculate the larger distribution angle with a stiff layer on the top. Okay, but we also can use the test. If we place the pressure cell here, you can back calculate the distribution angle. But this is under static loading. Okay, the simplified method for response model. And what happens if you have a cycle loading? But we develop the model. Basically said, initially the distribution angle is large. With the traffic loading, because of deterioration of the base course, the distribution angle getting smaller and smaller, eventually get higher pressure, it causes bearing capacity failure, right? But we basically did the test and measured the distribution angle, and for this is the control section, this is the biaxial geogrid, weak one, this is the biaxial geogrid, strong one, okay? So you can see if the slope getting flatter, means the distribution angle getting larger. Okay, but we developed this empirical formula. Basically, say the lambda is the distribution angle reduction rate. But if this equal to 0, means there's no reduction, basically like static loading. Okay, but with number of cycles, the distribution angle will reduce. But that lambda actually depend on 2 things: the geosynthetic products, and also depend on the base thickness. Okay. But if you have a thick base, this lambda is smaller. If you have a better geosynthetic, this lambda will be small. As what you see here, this is the one with a stronger geogrid. Okay, but this is the empirical method. Okay, with damage with traffic. But we assume that the tire is axis symmetric, circular. That we can calculate the pressure at this location use distribution method. But that pressure should be less than the bearing capacity factor. But we introduce the M's bearing capacity mobilization factor. Basically, depend on different rod depth, M will change. If you have a larger rod depth, M will be larger. Okay. But similarly, we have a bearing capacity factor for different situations, like controls 3.14, geotextile because a smooth interface of 5.14. And GeoCell is 5.14, Geogrid will be 5.71 because Geogrid provides a rough interface. Okay, but we came out of design chart, design formula like this. there's one important parameter with Geogrid called actual stability modules as ASTM standard. I will not get into detail to talk about the actual stability. Basically, this is the stiffness of the Geogrid. But we also developed a design chart and for that. But this is the one basically describe the geosynthetic property. Okay. But you need the iteration to determine the thickness of the base because you have a form of H on both sides. But this conversion is very quick. Typically, you need the 2 iteration can reach the solution. But if we know the CBR of subgrade is 1, if we go here with number of cycles, we can determine what the thickness of this case with Geogrid. Okay. This is my former PhD student, and he was working on the geocell. And for geocell, because we don't have the actual stability modules, but he recalibrate this factor, okay, with geocell. Okay, now let's talk about the case study here. But this is one case study is very interesting, actually, in China. And originally, they have the design with large replacement of the soil, like one is 1 meter, then the subbase, the base course layer. And because of the groundwater table is too close to the surface, when they excavate down, you have all the water, they need the dewatering. But they came out with the idea with use a 2-layer triaxial geogrid. As I mentioned, if the thickness is getting thicker, you may use 2 layers. But that reduced from 1.2 meter to 0.6 meter to avoid the groundwater table. Okay, but that is what you see here. Without the geogrid, the excavate down with all the water, you will not be able to do anything before dewatering. But if you use the geogrid option, you don't need to excavate that deep. Then you can have a dry surface. You can place the geogrid, place the aggregate, and you finish up with the road. Okay. So another case dealing with geocell. This is in Canada. This is the case dealing with basic peat organic soil. It's very soft, and they need to construct a road, unpaved road, with geocell. So here, basically, you see the geocell. When geocell transport the side, basically it's a collapse shape. After transfer the side, you need to expand it. Okay, this is the expansion, as you can see here. After expanding, you backfill with the soil. That's what they are doing here. But there is a special procedure in the follow. You need to fix the edge. Otherwise, the geocell will not stay open. Okay. Then you dump the soil on the inside geocell. Basically, they use on-site soil with sand, and then compact finish up, and it can carry a very heavy vehicle on this road, even though this is very soft peat material and can successfully carry the heavy vehicle with geocell stabilization. Okay, now let's move on to design with geosynthetics for stabilization of paved road. There are a little bit theory here, as I mentioned earlier on. There are 2 different design methods. One's 1993 ASHTO design guide. There's a statistical method. This is a mechanistic empirical design method. And basically this is based on the mechanistic and also empirical. But this is a pavement layer here. So basically for this method, you need to calculate called structure number, basically like structure capacity. But you have the layer coefficient to describe the quality of this material times the thickness of each layer. So we add together basically called structure number or structure capacity. Okay, so that layer coefficients relate to the modules of the layers. Okay, this is subgrade resilient modules. Now, based on the new design method, mechanistic empirical design method, basically use this formula to calculate accumulate the permanent strength. But in this calculation, this is the key. Basically, this is a resilient vertical strength, as I mentioned earlier on. Basically, this is based on layer elastic theory. Use Burmester solution. But if you can calculate the permanent strength for each layer modified by the thickness, and you add together, you basically calculate the rut depth. Okay, but this one will give you a rut depth, but this one basically give you the capacity. Okay, now how do we incorporate the geosynthetic in this method? Those 2 methods. But we propose, this is my former PhD student, propose a method basically to equivalent the modules. Okay, But we have a geosynthetic here, and with base course. But if we measure the pressure underneath, as I mentioned earlier, will get reduced, and you can measure the deformation on top also will get reduced. But if you equivalent to the one without the geosynthetic, but increase the modules, then you achieve the same performance, okay, as what is shown here. Okay, but if we can do that, then you can estimate what is equivalent the zero modules of the base course without the geosynthetic. Then you can use the method we talked about earlier on, 1993 design guide, or the mechanistic empirical design method. Okay, because in those two methods, they do not include geosynthetic. But we have to find a way, okay, to equivalent the modules for those methods. But if we know the equivalent module divided by the original modules, then we can calculate our modules improvement factor. Okay, and the module improvement factor can be determined from repeat triaxial test or larger scale cyclic plate loading test or trafficking test. Okay, but if we know the original zero modules, we get this curve. If we got the equivalent module for geosynthetic, we get this one. And the basic equivalent module is different from the measure modules as we talked about earlier on. But earlier on, as I mentioned, from the test, you will not get the increase the zero modules based on the elastic rebound because the geosynthetic will not provide the vertical strength. But in reality, the geosynthetic will reduce vertical stress, will reduce the permanent deformation. This is why we can back calculate based on the vertical stress measurement, back calculate based on the permanent deformation. Right? But that's what we did. We tried 3 different methods. So basically, we equivalent the vertical stress below the geosynthetic, equivalent the permanent deformation, equivalent the interface permanent deformation. But we back calculate the modules and the module improvement factor. But this is based on the vertical stress, interface stress calculation. But this is a non-stabilized. This is triaxial geogrid 1, triaxial geogrid 2. And with the thinner base, we calculate modules. And we also can calculate the back capture modules based on surface permanent deformation. And we also can back calculate the modules ratio based on the subgrade permanent deformation. And we also can check the different thickness, but their ratio is different. But as you can see here now, for the thinner one, you get a more benefit. And for the stronger geogrid, you get a more benefit. Okay. And but as you see here, for the stress calculation, actually the results not very consistent at the deformation. But we conclude the method in terms of accumulated permanent deformation are more reliable than those in terms of the interface stress. Okay, the reason the stress is only depend on the point and the deformation is accumulated. Okay, let me use this example to show you how do we consider the benefit of geosynthetics. But this uses 1993 design guide. Okay, it's a little bit easy to do. But let's say if we're base course the layer, this is the formula layer coefficient. But this is the zero modules. But if I know the zero modules, I can calculate layer coefficient. Okay, but if I have geosynthetic with modules improvement factor, then I can calculate the zero modules with geosynthetic. But let's assume the modules for control section 30 case SI. Now, unfortunately, this design method based on English. This is why I use the English unit. And then for the geosynthetic stabilized case, if I use the module improvement factor 1.5, then I get the 45 KSI. Okay, then I can calculate the layer coefficient for the first case without geosynthetic 0.14, with geosynthetic 0.18. Then I can calculate layer coefficient ratio. Basically 0.18 divided by 0.14, I calculate 1.3. But let's assume the case, this is statistical based design method, as I mentioned earlier on. But let's say the reliability is 95%, and there's a standard deviation, and then you go here, and based on the traffic, for this case, the 3 million equivalent axial load, and go this line here, and then you go to the turn line, and then based on the subgrade, okay? But for this case, because for the modules of the base course, we have 30 case SI, for the base course, if I go to 30, and I take the line here, go horizontal, and this is a serviceability loss. I will not get into detail about this. And then you go down, basically calculate the construction number. Now for this one, I calculate equal to 2.8, okay? But I know the asphalt layer coefficient is a very typical 0.42, but I can calculate the thickness of the asphalt layer, basically 3.2 divided by 0.4. I can calculate 6.7 inch, basically 0.17 meter, okay? Now I want to do a little bit different because this one below the base, the subgrade is equal to 5 KSI. But they take this line here, still go this line, and now we get the structure number for this one is 5.0, okay? The base cost layer coefficient 0.4 without the geosynthetics. And I go here, because we need to find the asphalt, or they take it was 2.8, the 5 minus 2.8 divided by 0.14, I calculate the base thickness 0.4 meter. Okay. Now, what happens if I use geosynthetics? For geosynthetics, basically the base thickness need to divide by layer coefficient. 1.3. Now I get 0.3 meters. As you can see, use geosynthetic can reduce 10 centimeter base course. Okay, but this is basically is a design method. You can figure out what thickness you need for base course with or without geosynthetic. Let me come back with the mechanistic empirical design method. You saw this figure before. Let me put the load here. But basically, I can calculate the vertical strength, and this is the vertical strength maximum value. The based on vertical strength, use a mechanistic approach, and then I can, use the empirical formula, can get the plastic strength here. So after I know plastic strength, then I can calculate rutting, I can calculate fatigue. Okay, that's empirical. But this method is actually an analysis procedure. What I mean, analysis procedure, you have to assume the thickness, then you calculate the rutting. Okay, but if your rutting not meet your requirement, you need to go back to change your thickness. But it's different from the original 1993 design guideline. They will calculate thickness for you. Okay, but this method you have to try and see whether it meets the requirement. That you adjust the thickness, you do the calculation like this. Okay, I'm close to the end of my presentation. I will show you one example about asphalt pavement reconstruction. But this is the border between USA and Mexico. The very heavy vehicle, and you see there's a rutting and the damage of the pavement. But they have an original design with the section like here, 180 millimeter hot mix asphalt with the class 2. Class 2 is high quality aggregate base, 750 millimeters. It's very thick. The subgrade, they use R value, but the equivalent CBI equal to 3. As I mentioned earlier on, based on Illinois design guideline, if the CBI less than 6, you need to do something, right? That's 3, but we need to do something. So for this case, this is a design that will reduce the asphalt thickness from 180 to 150, and also reduce the base course thickness, okay? And also use a little bit low quality aggregate. This is a class 4 aggregate called aggregate subbase, okay? But you reduce the asphalt thickness, use the low quality fill material, also use the thinner section, okay? So those are the benefits as we can see here. But in order to verify this design, they perform the plate loading test, as you can see here. But they test the deformation at the 2.5 millimeter and the 5 millimeter, and then test the 3 different conditions. One is basically Geogrid stabilized class 2 aggregate base over subbase. Okay, then we get this is the 24 kilonewton. This is 35 kilonewton for this 5 millimeter deformation. And if we test the subbase, the low quality subbase, we get a 24 here and get a 33 here. Now, if we don't use Geogrid, what will be the pressure or load is 19, this is 23. But if we were to compare, but this is 1.3 times greater in terms of capacity, this is a 1.5 times greater in terms of capacity, even though the Geogrid section is thinner and they use a low quality. Okay, but here basically show you the saving of the thickness and also how much is the cost saving here. Okay, but that's basically is $7.2 per square meter saving. Okay, so I'm going to reach to the concluding remark. Today, I share with you basically regarding the non-woven geotextile is effective in maintaining the properties of the base and the subgrade by separation, and is designed by preventing the loss of aggregate and the subgrade fines. But geosynthetic stabilized unpaved road allow that larger deformations are designed based on the bearing capacity, basically based on the strength. The benefits of geosynthetics are to increase subgrade bearing capacity and slow down the deterioration of the base course. But geosynthetic stabilized paved roads allows a small deformation can be designed based on the statistic and the mechanical empirical method, use the base equivalent modules as what I described. This is the current practice, basically current design with geosynthetic for improvement of road is in transition from empirical to mechanistic empirical method. Okay, but that's all what I have. Thank you very much. I think we have time for questions, right, Michael?
Yes, you're right. Okay, G, thank you very much for that very thorough presentation covering a lot of information on this topic. I think there's a lot of studying for people to do that when they see your handout, because you've included a great deal of background knowledge there. Also covering both unpaved and paved roads, and I think it's very nice how you've emphasized the differences between the two, especially in the approach to design. Yeah, so we have 4 questions so far. I've been looking at these as they come in, and I'll start at the top and work down, so you can also read them if you wish. But this is from Ferdinand. He says, thanks for your presentation. What are the different mechanisms of crack propagation in asphalt overlays, and how can geosynthetics be beneficial in preventing such cracks? It's a very good question, that really aimed more obviously at paved roads.
Yeah, I did not talk about this. I mean, in the pavement application, really, we can use geosynthetic for many different things. And as I mentioned, we can use it for concrete pavement. I mean, if we have time, I can come back and talk about use geosynthetic for concrete pavement. And also you can use geosynthetic for overlay mitigation, the cracking mitigation on the overlays. But basically for mitigation of the cracking on the overlay, basically there are 2 different mechanisms, right? One basically use interlayer, basically try to make interlay is impermeable. That basically stop the water to get into the subgrade or base course. Okay, so that is one way to do. Basically, they replace the geotextile with asphalt and generate the basically impermeable layers. Another thing is we typically use the glass geogrid, is a stiff geogrid, and then try to use as a reinforcement and to mitigate the overlay, the movement with the underlayer pavement or cracks. And that's the 2 different ways to do. Actually, we are working on the research now and to try to test the geogrid interlay for concrete pavement overlay situation with asphalt.
Yeah, thank you. Good response. Actually, it might be worth people knowing that you referred to some of the research of Professor Brown from years ago. He did an awful lot of research also on asphalt and the effect of geogrids and geosynthetics in asphalt overlays. So if people want to look into that, then there's a lot of information. Another question from Rocky. He says, good morning, Mr. Hahn. Thank you for your amazing presentation. I have a question. Which geosynthetic do you think is more recommended to bear the cyclic loading on paved and unpaved road? Geogrid or Geocell?
Okay, very good question. Both products will work, right? And as you know, GeoCell uses more plastic. You can imagine GeoCell will be more expensive than Geogrid, okay? Then for some situation, GeoCell may work better, especially if you're dealing with some material cannot interlock well with Geogrid, okay? The typical Geogrid, we use aggregate, okay, with certain size, as I mentioned, you know, the interlocking between aggregate and the Geogrid is very important to, you know, you get the lateral strength. GeoCell works a different way because you have a pocket. Everything, you know, put inside, put infill material will be confined. But if you have like a river sand, okay, then we did a study in the United States and we tested with the river sand, you know, because you have a round particle, uniform particles, and if placed in the GeoCell will be confined. But that probably will not interlock well with Geogrid. Okay, for that situation, then GeoCell will be better. But you will use the more expensive products as compared with Geogrid. But really, it's dependent. The answer is dependent on your situation and depend on what material you have. You know, on site, if you want to use on-site sand rather than to import the aggregate for some situation, sometimes GeoCell will work well. But for most cases, I think Geogrid will work better in terms of economic as compared with GeoCell.
All right, thank you, G. We have we just have a comment here. Avik Kumar, who actually I'm sure is listening from India. He just says, very interesting, detailed, and thoughtful presentation, Professor Han. Regards. So no question there, just a very nice compliment. And also from Ispamo, who's actually in the office here. He says, thank you, Professor Han, for an interesting presentation. And then he has another question related to GeoCell. Is it reliable using GeoCell in swampy areas as a stabilization material? So we here in Indonesia, we have a lot of swampy areas, and it's a common problem to build roads across them.
Yeah, for the project I mentioned to you in Canada, it's just kind of swamp area. Now, for that case, you need to place geotextile first underneath the GeoCell. Okay, otherwise, it will not hold the field inside the cell. And also for that project, they use 2-layer GeoCell. Okay, to deal. It's very, very soft soil, but after they finish, you basically support a very heavy vehicle. You can do it, but you will need the geotextile on the bottom before you place the GeoCell.
Yes, I think just I mean, my observation, the difficulty on swamps is really placing the materials. Obviously, rolling out materials is probably easier than trying to place the GeoCell structure, and therefore you might need to, as you say, to get some initial layer, I'd have thought, before you try to do it. But yeah, the swamps here can be quite bad, and it is quite a big problem. We have from Patnur Zaman, who's also in the office here. He says, thank you for an amazing presentation. He has no question for you, but we have another one here. This is from someone with a similar name, Han Yong John. I'm sure he must be from Korea. So thank you very much for the nice presentation, Dr. Jihan. How do you think about applying 3D geotextiles?
3D geotextile.
Yeah.
Okay, I try to think about 3D geotextile. I know there was some study done in China as well, and they try to produce this 3D geotextile. In the past, I think it's difficult to manufacture, but now the situation may be changed because now we have what's called 3D printer. Maybe we can print a 3D geotextile in that way. I'm not sure that having enough research done about this, but I try to imagine if you use 3D geotextile, I think there probably will improve the interlocking between the aggregate with geotextile. Basically, you kind of like you place Geogrid on top of geotextile. It's kind of like a 3D situation, right? That probably, yeah, that is possible. But I don't think we have done enough research for this now. But this is the interesting idea.
Okay, so and then our friend Mr. Hahn, he asked a supplementary question. He said, for the cushioning effect, he's thinking therefore about 3D geotextile for a cushioning effect, which of course can be an application in some situations, but it's not. I think it's not really in the area of roads, but I don't know what you think about that.
Cushioning effect. I mean, I think this is talk about more like a stress distribution kind of things. The people analyze, actually, as I presented as well for the two methods I mentioned, right? Store method, Dr. Giroux and I developed a method, both based on the stress distribution. And sometimes people consider, use geosynthetic will increase the distribution angle, and that may be considered as kind of cushioning effect. Maybe use like 3D geotextile, you can increase the angle more than 2D geotextile. I think that's what the person maybe is thinking. That is possible.
Okay, right. No, thank you. That's we have another comment and question from Jakob. He says, "Great presentation. Thank you, Professor. One of the geotextile properties is elongation. How can we use this in designing unpaved roads?"
Typically, we don't use elongation in the design because either for tension membrane effect is what I'm talking about, and you really, if you want to mobilize the tension, you really want to have a less, deformable geosynthetics, or you can say the stiff geosynthetic, we can mobilize more tension. And for interlocking, also you prefer to have a little bit stiffer geogrid, then you can provide more interlocking. Now there may be some benefit with some kind of elongate geosynthetic during the construction, and if this is material too brittle and during the construction, you may get more damage, right? But if you use the geosynthetic with more elongation, you may not damage it for that. For geotextile, for separation purpose, sometimes this is why we use non-woven geotextile, because non-woven geotextile can elongate more than woven geotextile, right? And of course, another reason maybe non-woven geotextile is cheaper than woven geotextile. That's another reason, but also filtration purpose, also non-woven geotextile is better. For separation, because of the installation damage may create a problem, as I mentioned, the serviceability, serviceability of geotextile. That maybe we need the elongation, but in terms of tension membrane, lateral strength, we don't use elongation because that deformation will be too large.
No, thanks, G. Actually, we have a very nice comment from David Duff here, which I think I'm going to ask a question from it, but he says, "Excellent presentation. We are on the way to enabling the design for new roads and justification for and acceptance by road authorities." He says, "Thank you very much." Now, actually, this is a very good point. And what's your experience then on acceptance of geosynthetics within road authorities? I guess yours is mainly in the US in recent years, but this can often be, if you like, a hindrance to development because some road authorities concerned about them. And actually, we very much rely on all the wonderful work that you do and similar colleagues who do research into these things to help provide information to justify them. And that often is something we need to convince road authorities. But if you had any words to say about that, I think that's very useful because, of course, we have road authorities here in Indonesia who certainly make use of geosynthetics, but I think they have a much bigger role to play myself. And I'd love to hear what you have to say about that, G.
Okay, I think this is a really, really good question. I think we are on the same boat for some degree. And in US, we have a similar problem. Like say the design method I talked about 1993 and the new ME design method, there's no geosynthetic included in the design method. And I don't know when they did have geosynthetic included. But the industry, I think geosynthetic industry does not want to wait, right? But basically, we have been working with geosynthetic industry trying to modify the design method. But that's what I'm presenting to you today, basically regarding the equivalent modules method. Because basically, you don't need to change the design method. But if you can come out with equivalent modules, just use the current design method. But I think that will be easier for law authority to accept. Basically, you use the same design method. Otherwise, if you come out with a different method and people are not sure this method is valid for different products, all those kind of things. But this is something, this is why we come out of this approach. Basically say, you test it based on the permanent deformation, you back calculate the equivalent modules, and then use exact same design method as what we have. Okay, I think in U.S. DOT, the state DOT is a little bit flexible than the federal, the ASHTO, and they allow the some designers or the geosynthetic industry to design road for them. But for unpaved road, it's not a big problem. For paved roads, I think it's a little bit more challenge because if you're dealing with a highway, it's a little bit difficult to sell.
Yeah, no, I'm sure that's the case. I mean, just out of interest, currently in the US, how many of the state DOTs are very accepting of new ideas and technologies? I don't think it's all of them, is it? But I think some of them are very forward thinking and do accept things readily. Others are a bit slower. I think, is that the case?
Yeah, I think some DOT, like Minnesota DOT, they have the test road, and they have a very strong pavement material group, and they test the geosynthetics there, and they came out with some kind of design procedure. But if DOT develops some design procedure, they will use it, right? And often, if the design procedure come from other people, especially come from industry, I think that the authority will be a little bit resistant to use it. That does not mean that the method come out from industry is not good, but this is just the situation, right? People try to accept more, academic research or that kind of things, right?
Well, exactly. We're very much relying on people like you to do that, G. So that it's wonderful that there is so much research available and so many excellent publications, and I think we all appreciate that very much. Just one, I think it's probably the last question here from Kien Trung, I guess from Vietnam. He says, thank you very much, Professor Han. Your presentation is amazing. As usual, he must have listened to you before. He says, I have a question. I understand that the triaxial geogrid and geocell both provide the confining effect. Please give some advice to choose between these two products. Many thanks. Similar question, I think. Yeah.
Yeah, I think this is a similar question. I mean, the answer is basically depend, right? And as I mentioned, depend on what kind of base course material you have, and depend on the cost, and also depend on what kind of design you have. And really, it's a dependent situation.
No, you're right, of course, yes. Yeah. No, that's always going to be the case. Well, I think that brings us to the end of the questions. I find, we'll just try and fit this one in. Then this is from Keanu Shatami, I'm assuming being from Japan originally. He says, hi, G, he must know you, I think. Very informative presentation. I was wondering if you also comment on the work that Steve Perkins did in 2004 on implementing GS in ME design. So this is geosynthetics, I guess, in ME design in comparison to your method. Okay,
yeah, I think that the method he mentioned about Steve Perkins, basically in Steve Perkins' method, he incorporated called residual stress or compaction or trafficking induced stress. And I think that the concept is wonderful, and there's a little bit challenging to determine the residual stress under different situation. The way he proposed basically use approach like a temperature change. Like I try to remember, like change 1 degree temperature, and then you create the pre-stress condition to simulate the residual stress induced by traffic or compaction, that kind of things. And we did something as well with GeoCell, and we used the Duncan seed approach, use the stress path to estimate the residual stress after compaction. And I just found, I think that the Steve Perkins method is a little bit difficult to implement, determine the residual stress. I think the concept is wonderful, as I mentioned. We also adopt that concept for one of the study, and but just how do you estimate the stress? That is the question.
Okay, I think, oh, there's and he just says, thank you very much. Okay, well, I think that's brought us to the end of the Q&A session, G, and both all your answers and your original presentation have given a huge amount of information. As I said at the introduction, I think my internet wasn't so good, so I'm in a different place now for better internet.
Yeah, you did.
Anyhow, I think it's very valuable. As I mentioned earlier on, we haven't had in our webinars of the Indonesian chapter of IGS, we haven't had many presentations in the area of pavements, and really you've given a very comprehensive summary there. I think people should be downloading the PDFs of your presentation and studying that if they'd like to learn more, because so much wonderful information stored away in your slides and with guidance to go elsewhere. And I think people should find that extremely helpful. Just to let you know, we did have a very nice session from Jorge, concentrating on expansive soils. I'm sure you'd realize that. And also Errol talked to us, but that was aimed at railway. So we have had some presentations aimed at more the pavement application, but yours is the first to give what I could say is a comprehensive overview, both paved and unpaved. And as I mentioned just now, very nice to see how you've emphasized the important differences between basically the strength of subgrade and a failure condition compared to looking at deformation as the principal targets of the design method. So I think this is very good guidance for people, and I'll certainly look forward to having another look over your slides when I can see them as well. Anyhow, I will bring your input and my input to an end now, G. Just to thank you yet again for all the hard work you've done in assembling this, and we'll look forward to seeing you again, we hope, in Indonesia before too long, if that's possible.
Sure.
And please, you're now in your early evening. Of course, everyone should know that G is obviously speaking from the US, so he's approximately 12 hours difference. So please enjoy the rest of your evening. If you want to listen into the quiz, of course, you're most welcome. You just follow the instructions. You'll do it on your mobile phone or in your computer. You go to a website and do that. And just say goodbye again. Thanks again very much. And hopefully we'll meet up again before too long.
Thank you very much, Michael, for your moderation and for kindness, introduction, all the questions. Very good. It's my really great honor. Look forward to visit Indonesia.
Yes, please.
Soon.
The honor is ours. Okay, bye, G. Bye-bye.
Okay, bye. Thank you.
Once again, thank you, Professor Jihan, for your excellent presentation. And thank you also to Bapak Michael Doby for guiding the session. Now we are heading to the quiz session that will be guided by Ms. Rifa. Please welcome Ms. Rifa. The time is yours.
Thank you.
Okay, thank you, Stephanie. So hello everyone, I hope everyone is in a good health today. As usual, I would like to invite all of you for the chance to get a very interesting prize by joining a very short game we have prepared. The questions is from Prof. Jihan, and the first winner will get 150,000 rupiah, and the second winner will get 100,000 rupiah. To give you a disclaimer before we play, everyone can join this quiz, but for technical reasons, only those who live inside Indonesia are eligible to get the prize. So you can now directly go to your browser on your phone or your PC and then type menti.com, MENTI.com, And you have to type the code number shown on your screen or also there in the chat box. The code is 21820779. Once again, go to menti.com and put the code 21820779. Then fill in your name and make sure it is the name you submit in the registration for this webinar. So later, if you win, the committee will easily contact you for the prize. Remember, the prize is very interesting, the total of 250,000 rupiah, and you will not want to miss this chance. For those who live inside Indonesia especially. So go to menti.com, put the code 21820779 and fill in your name. So let's see how many people have already joined our game. Okay, let's play. We have 49. I'm still waiting for the others for another minute. Please go to menti.com and then fill in the code 21820779. You can see it on your screen and they're also in the chat box. Okay, we have 51 people joining in. Okay, it keeps increasing. I'm going to count down now. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Time's up. Okay, I'm going to start the quiz now. Yeah, 62 people. First question, answer fast to get more points. Geosynthetics are more beneficial to improve performance of roads on, is it the first option, soft subgrade? Is it the second option, firm subgrade? Or is it the third option, lime stabilized subgrade? You still have 30 seconds, but you have to answer faster to get more points. Today, we're gonna have two winners. The first winner will get 150,000 and the second winner will get 100,000. So for the first question, geosynthetics are more beneficial to improve performance of roads on soft subgrade, firm subgrade, or lime stabilized subgrade. The time is now 5, 4, 3, 2, 1. Time's up. Let's see. The correct answer is the first option, soft subgrade. Let's see for the first question, who leads the points? Let's see the leaderboard, but not yet winning, yeah? For the first question, is led by Asmi Lisani Wahyu. Let's go to the second question without further ado. Question 2 of 3. Answer fast to get more points. Is stronger geogrid always better than weaker geogrid to improve road performance? Only two options. Is it yes or is it no? Is stronger geogrid always better than weaker geogrid to improve road performance? You have two options. Is it yes or no? You still have around 20 seconds, but answer faster to get more points. Only 2 people will get the prize. And only those who live inside Indonesia will be eligible to win the total of 250,000. Okay, 5, 4, 3, 2, 1. Time's up. Let's see. The correct answer is no. Okay. Now we see. Let's see who is leading. Oh, I think it's changing the leaderboard. Let's see. The fastest one is Samuel, but the leaderboard is led by Ronnie. You still have one more chance to catch up on the leaderboard to see who will win the total of 250,000 rupiah. Only 2 winners. Last question. Under traffic loading, geosynthetics are most effective in reducing, is it the first option, elastic deformation? Is it the second option, permanent deformation? Or is it the third one, resilient deformation? You have 3 options. The first one, elastic deformation. Or is it permanent deformation? Or is it resilient deformation? You still have around 20 seconds, but answer faster to get more bonus point. Under traffic loading, geosynthetics are most effective in reducing. Is it the first, is it the second, or is it the third? Okay, let's see. 5, 4, 3, 2, 1. Time's up. And the correct answer for the last question is the second option, permanent deformation. Let's see who will win today's quiz. 2 winners. We will have 2 winners. Let's see. So congratulations to the first winner is Ronnie with 2,929 points. Will get 150,000 rupiah, and the second winner is Sri Kanti with 2,927 points, will get 100,000 rupiah. Okay, you can contact the committee, or later committee can also contact you. Thank you everyone for playing with me. I hope you had a good time. I'm going to give the event back to Stephanie. Thank you everyone.
Thank you, Ms. Rifa. And that's it for the quiz session. And congratulations for the winners. Next, for the upcoming webinar, we would like to invite you to the 7th INA-IGS Geosynthetic webinar under the theme Raising the Bar, High Technical and Environmental Performance with Multifunctional and Sustainable Geosynthetic with engineer Pietro Rimoldi, civil engineer consultant from Milano, Italy. The webinar will be held on next month, August 24, 2022 at 6:30 p.m. GMT +7 or Jakarta time. You can register by visiting the link bit.ly/INA-IGS AUG 2022 are also shown on your chat box. Ladies and gentlemen, we have now reached the end of the event. Before you leave this webinar, we would like to inform you that you can access your e-certificate and soft copy of material from the speaker by visiting the link bit.ly/INA-IGS July 2022 after filling out the quick survey. You will be redirected to the e-certificates. Once again, thank you for your participation. We hope we can see you in the next webinar. Finally, I wish you a very good day. Stay healthy, everyone. See you.